Hello, hello, I'm Breton, one of our MCAT tutors here at Inspira Advantage, where we help students get accepted into med school and other professional programs. Today, we are quickly going to go over the difference between an Arrhenius, Bronsted-Lowry, and Lewis acid, so that you can better be prepared when the MCAT asks you to do this on your own. We're also going to end with 2 guided practice problems, so that way you can test to see if you're learning. The way that we are going to go through this is chronologically, where we start with the oldest definition of an acid, the Arrhenius acid, and move on to the modern definition, the Lewis acid, or Lewis base. Starting down here with the Arrhenius acid. An Arrhenius acid is a compound that produces H+. It produces a free hydrogen when reacted with something else. On the flip side, an Arrhenius base is a compound that produces an OH- when reacted with something else. So, what does this really look like? Let's take a look at this short little figure I've drawn out here. Water is an interesting molecule, beyond being the most important molecule to life. Now, it's not clear just looking at it to see if it's an Arrhenius acid or a base, until we split it up into its component parts, which I've done right here. In blue, we have essentially a hydroxide, and in red here, we have the hydrogen atom bound to the hydroxide. Well, when water just dissolves in itself, we're going to see we get these 2 products on the right, our blue hydroxide and our red H+. Well, what is water then? Is it an Arrhenius acid or Arrhenius base? It's actually both, because it can produce a H+ or it can produce an OH-. And since it's doing both of these things, water is actually both a Arrhenius acid and an Arrhenius base. So let's now look at a more easily visible example of an Arrhenius acid. So looking down here at our HCl, or hydrochloric acid, we'll see that when we dissolve HCl in water, it is readily going to give up a hydrogen as well as a chlorine. We can see that HCl, because it's producing an H+, it must be an Arrhenius acid. Is chlorine an Arrhenius base? No, it cannot be an Arrhenius base because it's not producing an hydroxide. Now, it might be a different type of base, but we'll get to that later. For now, we're just focusing on Arrhenius. This is an Arrhenius acid, but not an Arrhenius base. Other common Arrhenius acids you will recognize are those strong acids that you memorized in general chemistry. For your ease, I have those listed out on the left right here. Now, conversely, the strong bases, anything that is producing a hydroxide, is going to be an Arrhenius base. So whenever we see strong acids or strong bases, I want you to be thinking, okay, this is an Arrhenius acid or an Arrhenius base, if it's strong. And the nice thing about starting with Arrhenius is that if you understand an Arrhenius acid, then you will also understand the Bronsted-Lowry acid. Why? Because they are the exact same thing, the exact same definition. Bronsted-Lowry acid, it's just donating a proton, just giving up a good old H+. Now, bases are a little bit different. For Bronsted-Lowry, it's a proton-centric world. They define a base as the molecule which accepts a hydrogen. Okay, so all we care about is that bases accept hydrogens. Okay, so let's look at what this might mean. For my example here, I've just drawn this acidic molecule over here. On the left, this part right here, this is a carboxylic acid functional group, really key functional group to know for the MCAT. And on the right here, I just have some nitrogen compound. So I've drawn out the organic chemistry reaction of what's actually going to be going on here. So let's say we've got our nitrogen right over here. Just going to go over here, grab that hydrogen. Once it grabs the hydrogen, that bond is going to go onto the oxygen and leave us with a compound looking something like this. Let's talk about what's going on the left. We can see the hydrogen donor. For me, this is the easiest part to see. Okay, I can just find the hydrogen, see where it's going. Well, this hydrogen is coming onto the nitrogen. The hydrogen is being donated. If it's being donated, someone must be accepting it. If you're going to go donate clothes, somebody has to accept the clothes you're donating. The person accepting those clothes, or in this case, accepting the hydrogen, is going to be the Bronsted-Lowry base. So that's all that this nice nitrogen group is. And then just for the sake of getting a double whammy review, to the right here, what was once an acid is now the conjugate base, and what was once the base is now a conjugate acid. And this will be true of any of your acids or bases, whether that be Arrhenius, Bronsted-Lowry, or the Lewis acids. It can be tough to spot the Bronsted-Lowry base, but if you make sure to follow the hydrogen, you'll be able to find its acceptor, and therefore you'll know what the base is. Now, finally, we get to the Lewis acid theory of acid and bases. This is the most widely accepted and modern theory of acid-based chemistry. While the oldest method, Arrhenius, focused on if H plus or OH minus was being produced, and Bronsted-Lowry only cared about who was donating or accepting those hydrogens, Lewis is focusing on something much smaller, electrons. The Lewis theory is similar in principle to Bronsted-Lowry, but it is reversed in a way. An acid is going to accept a pair of electrons, whereas a base is going to donate them. What helps me remember this is going back to the foundations of Arrhenius. The charge on an OH is negative, and negative OH has extra electrons. That's what's making it negative. Well, then it has to be donating those extra electrons to something else to help it stabilize. This is exactly the type of thinking you want to master for the MCAT. So let's take a look at this even more clearly. Here's that hydroxide I was talking about. We've got 1 electron pair, 2 electron pairs, 3 electron pairs. That's too many for oxygen. That's why it has this negative charge. To get rid of these electrons, it's going to donate them. So that's exactly what I've shown in this white arrow here. We're donating those electrons, snatching a hydrogen away, breaking the bond on that OH3 group to go back to the oxygen. So what are we going to produce in this reaction? Good old water and water. And if you really wanted to be a purist, you could write it H2O, but I just wanted to make it very visual here. We can see that the one that's donating the electrons, our hydroxide, is going to be a Lewis base. The electron acceptor is going to be a Lewis acid. And this one is nice and straightforward. This one is easy to see. But as you know, the MCAT is not going to just give you easy questions all the time. They're going to make things tricky. So what happens if I remove the hydroxide? Can we still follow through with what is going on? Let's talk this through. Let's see if we can. If we have this B3Fs, we've got a boron and 3 fluorines. Reacting with this, we're going to have just kind of a good old NH3 over here. And I've explicitly drawn in the electrons. So again, we've got a lot of sources of electrons. Now, how are we going to know which one we want to bind? It helps to see the reaction, which oftentimes the MCAT will give you. So I'll show you the end product. If we're trying to create this end product over here, let's think about what type of reaction we want to conduct. Join right there. It looks that simple. There's no leaving reaction. It's just simply adding this nitrogen group to the boron. Well, let's think this through then. Who is our electron donor? Right here. It's literally donating. I'm going to point this even closer. We are donating these electrons. Acceptor? Well, that's going to be our boron right here. The boron is accepting those electrons. Based on our definition then, the electron acceptor is going to be the acid, and the nitrogen is going to be the base. So those are the foundational fundamentals for you. So here is a whole zoomed out version for you to grab a screenshot and study from. I want to thank you so much for watching our video on the different types of acids and bases, and I'll see you next time.